You have spent 3 days scraping fat from an animal hide. If the hide is not cleaned before it dries, it may stiffen, rot, or begin to smell strongly enough to attract insects and scavengers. So you carry it to the river. You rinse it. The blood loosens. The mud runs away, but the grease remains. Water slides across it as if the dirt is protected by an invisible skin. You rub harder. The fat spreads. You add sand. Now the hide is scratched but still oily. Nearby, rain has fallen into the cold ashes beneath an old cooking fire. Melted animal fat has dripped into the same gray paste. You touch the mixture. It feels slippery. You rub it across the hide. And suddenly, the grease begins to release. The water, which could not touch the fat before, can now carry some of it away. You have discovered something powerful. You have also discovered something dangerous. The same ash water that removes grease can burn skin, damage hair, and destroy the material you are trying to save. If the mixture is too weak, nothing happens. If it is too strong, it injures you. If the fat and ash are combined incorrectly, the result remains oily, caustic, or useless. And because the active ingredients vary from one fire plant and animal to another, success is difficult to repeat. This is the real problem behind the invention of soap. Not simply how to become clean. Humans had washed with water, rubbed themselves with sand, scraped their skin, and used cleansing plants long before the first written soap recipe. The deeper problem was how to make water remove what water naturally rejects, oil and water separate. Grease clings to skin, wool, and tools. Soap works because each molecule behaves like a tiny negotiator. One end joins water, the other reaches into oil. Humans did not invent cleanliness. We invented a chemical bridge between two substances that refused to mix. But the first people who made that bridge could not see molecules. They had to discover the reaction by smell, touch, heat, failure, and pain. And the earliest surviving evidence suggests they may not have been trying to wash their bodies at all. They were trying to clean wool. A modern bar of soap has trained you to expect bubbles. Rub, lather, rinse, clean. But foam is not the beginning of hygiene. For prehistoric people, cleanliness was not one idea. It was a collection of practical problems. Mud could be washed away with water. Dried tissue could be scraped from a hide. Hair could be combed. Smoke could discourage insects. Sand, clay, and crushed minerals could absorb oils or create friction. Some plants released compounds that foamed when beaten in water. Soapwort, soapberries, and other sapin-enriched plants can reduce surface tension and help loosen dirt. Modern chemical research still studies their potential as natural surfactants. These methods do not require true soap. That distinction matters because the history of soap is often told as though humans were filthy until someone invented a bar. That is backwards. Humans were already highly attentive to smell contamination, parasites, appearance, and the condition of skin and clothing. A bad smell could signal rotting food, an infected wound, spoiled water, or a person who had been near death. Clean hair and prepared skin could communicate health status, ritual readiness, or sexual desirability. A washed textile could accept dye more evenly. A cleaned hide lasted longer. The pressure to remove dirt existed long before anyone understood the chemistry. But different forms of dirt demand different solutions. Dust can be brushed away. Salt dissolves in water, grease does neither. Grease is especially difficult because it can trap other material against a surface. On wool, the natural fat called lanolin protects the sheep but interferes with spinning and dyeing. On cooking vessels, animal fat holds soot. On skin oil, combines with sweat dust and particles from work. Water alone cannot efficiently surround and carry these oily substances away. So humans experimented with materials that seemed to weaken grease. Ash, alkaline earths, plant extracts. Urine allowed to become alkaline, oil, fat, heat. The person doing the work did not need a theory of molecules. They needed to recognize a transformation. A liquid changes texture. A stain begins to lift. A greasy surface becomes easier to rinse. A repeated practice becomes a recipe. The first soap maker may never have thought, I am inventing soap. They may have thought, this cleans wool better. That is how many technologies begin. Not as an answer to the question history later asks, but as a solution to a smaller problem someone could no longer ignore. To understand why soap was so difficult to invent, imagine trying to carry oil through water without touching either one. Water molecules are attracted to other polar molecules. Most grease is nonpolar. When water meets oil, the two separate because their molecular structures do not interact comfortably. This is why rinsing a greasy hand can make the hand wet without making it clean. Soap changes the negotiation. A traditional soap molecule is a salt of a fatty acid. It has a water-loving or hydrophilic head and a water-avoiding or hydrophobic tail. The tail is comfortable inside grease. The head is comfortable inside water. When many soap molecules enter water, their tails can gather around oily material while their heads remain exposed to the surrounding liquid. They form tiny structures called micelles. The grease becomes trapped inside. Now water can carry away something it previously rejected. The soap does not need to make the dirt cease to exist. It changes who the dirt can travel with. This is the central trick inside every traditional bar, and humans discovered the trick through a reaction called saponification. Fats and oils are largely built from triglycerides. When they react with a sufficiently strong alkali, the fat molecules are broken apart and converted into glycerol and fatty acid salts, the substances we call soap. Different starting fats produce different results. A soap made from one oil may be hard and slow to dissolve. Another may be softer. Some lather easily. Some clean aggressively. Some leave skin feeling less dry. The alkali matters too. Sodium-based soaps tend to produce harder bars. Potassium-based soaps tend to be softer or more soluble. But an early soap maker had none of these words. There was no triglyceride, no fatty acid, no micelle, only signs. The mixture thickened. The shine of free oil disappeared. The liquid bit the skin less than the raw lye had. A cooled mass could be cut or scooped. That meant soap making was a form of blind chemistry. The craftsperson controlled substances whose active structures were completely invisible. They learned the reaction through consequences. Too much unreacted fat and the product stayed greasy. Too much alkali and it remained caustic. Too little heat and the transformation slowed. Too much water and the product became weak. The invention was not a lucky mixture of ashes and fat. It was learning to control the boundary between a cleanser and a chemical burn. Soap leaves a frustrating archaeological record. A bronze blade can survive for thousands of years. A clay jar can break and remain in the soil. Soap dissolves, decomposes, and disappears. That means the history of early soap cannot be reconstructed from a line of ancient bars waiting in museum cases. Chemical historians must often depend on texts. In 2015, chemists Kristine Konkol and Seth Rasmussen reviewed the evidence for soap production in antiquity. They emphasized that the earliest known evidence comes from Mesopotamian clay tablets in the third millennium BCE. The oldest literary reference they discuss concerns the washing of wool and dates to around 2500 BCE. The text is connected with Girsu, an ancient city in what is now Iraq. This is not a recipe for a pleasant bath. It belongs to textile work. Fresh wool contains lanolin, dirt, sweat salts, plant fragments, and material gathered from the animal's environment. Before wool can be dyed and transformed into valuable cloth, much of that contamination must be removed. An alkaline washing material makes the process easier. Chemical historian Martin Levy drew attention to these ancient technical texts while reconstructing the chemical knowledge of Mesopotamia. The evidence does not present one dramatic inventor. It reveals an industry. People were managing fats, ashes, alkalis, water, and textiles with enough consistency for the process to enter written records. That changes the usual image of soap's birth. The first documented soap-like cleanser was not sitting beside a bathtub. It was inside a workshop. The user may have cared less about fragrance than whether expensive wool accepted dye evenly. And the substance may not have resembled a modern bar. Ancient terms can refer to alkaline washing agents, soap-like mixtures, or related cleansing materials, whose exact composition is difficult to recover. Translation is not chemistry. A word on a tablet cannot tell us every ingredient. Konkol and Rasmussen therefore warn against pretending the evidence is cleaner than it is. Soap may have formed before the third millennium BCE from the simple combination of plant, ash, and animal fat, but no empirical evidence currently proves an earlier date. This uncertainty is important. The invention of soap probably did not happen at one moment. People may have created soap accidentally many times. The true breakthrough was recognizing that the slippery substance was useful, then learning how to produce it deliberately. The tablet preserves the point at which an invisible reaction had become part of organized human knowledge. How could the first true soap have appeared? No surviving witness can tell us, but the chemistry allows several plausible routes. Animal fat frequently entered fires. It dripped from roasting meat. It coated cooking vessels. It collected in workshops where skins, wool, perfumes, or oils were processed. Wood and plants left ash containing alkaline compounds. Rainwater, washing water, or deliberate soaking could carry those compounds into solution. Bring enough fat and alkali together, add heat and time, and some saponification can occur. That does not mean the familiar story of fat dripping into a sacred fire and producing perfect soap is historical fact. It is a possibility, not evidence. Accidental soap would often have been weak, contaminated, or dangerously alkaline. Most ash and fat mixtures do not automatically become a pleasant cleanser. The real discovery required comparison. A worker notices that one ash cleans better than another. Ash from certain plants produces stronger alkaline water. A vessel used before seems to improve the next batch. Heating changes the texture. A measured amount of fat reduces the burning quality. A longer boil creates a more uniform product. These observations become craft knowledge. One person may know which plants to burn. Another may recognize when the lye is strong. Another may understand when the mixture has cooked long enough. The recipe can exist without numbers. Use this basket of ash. Fill the pot to this mark. Boil until the paddle leaves a trail. Add fat until the sharpness changes. Let the mass rest until it separates or thickens. This is chemistry stored in the body. The hand knows the weight. The eye knows the surface. The nose recognizes the change in odor. The skin becomes an instrument, sometimes painfully. Soap making may also have developed from other cleansing technologies. People already used plants rich in natural surfactants. They already treated textiles with alkali. They already processed oils and animal fats. The invention did not require a leap from ignorance to science. It required several existing practices to collide. Grease was the problem. Ash was one tool. Heat accelerated change. Water carried the alkali. And repeated work revealed that the ingredients could produce a new substance rather than merely sit together. The first soap maker did not create matter from nothing. They taught waste products from food and fire to cooperate. The most dangerous ingredient in early soap making was not the fat. It was the alkali. Ash may look harmless after the fire is gone, but water passing through suitable ash can dissolve alkaline salts. The resulting liquid may feel slippery because it reacts with oils on the skin. At higher strength, it can damage tissue. This created an ancient measurement problem. How do you judge the power of a liquid you cannot see? The color may change little. The active concentration depends on the plants, soil, temperature, burning conditions, amount of water, and how long the solution remains in contact with the ash. Two fires can produce two different alkalis. A successful recipe using one batch may fail with the next. Later, soap makers developed practical tests. They judged whether an object floated. They observed how the liquid affected feathers, eggs, or other materials. They tasted or touched substances in ways no modern safety system would permit. These methods did not measure pH. They created repeatability. The craft also had to control the fat. Animal tallow contains a different mixture of fatty acids from olive oil. One hardens differently. One lathers differently. Impurities change odor, color, and texture. Salt can help separate soap from glycerol-rich liquid in some processes. Cooling can reveal whether the mass will become a bar or remain soft. Soap making, therefore, became a chain of decisions. Burn, leach, strain, heat, add, stir, wait, separate, cut, dry. At every stage, the maker could lose fuel, oil, labor, and valuable fat. A failed batch was not merely ugly. It represented food, light, and stored energy that could no longer be recovered easily. That cost created specialists. A community might make simple household soap from waste, fats, and ash, but producing a consistent, mild, transportable soap demanded experienced judgment. The craftsperson had to transform a corrosive, liquid, and greasy material into something safer than either ingredient. This is the paradox inside soap. The cleanser is born from two substances you would not normally rub on your skin. Raw fat makes you oily. Strong lye can burn. React them correctly, and each helps neutralize the problem of the other. The invention was not mixing opposites. It was knowing when the opposites had finished changing. Soap existed in the ancient Mediterranean world. That does not mean everyone used it to wash the body. Greek and Roman bathing followed a different logic. Athletes and bathers could rub olive oil onto the skin. Dust, sweat, and dirt became trapped in the oil. Then a curved metal tool called a strigil scraped the mixture away. Museum images show athletes carrying oil flasks and strigils. The method sounds strange to someone raised with soap, but it solves the same problem through another route. Instead of persuading grease to enter water, you dissolve dirt into oil and physically remove the oil. Roman bath culture became elaborate without making the modern soap bar central to bodily washing. This creates one of the most surprising clues in the history of the word. In the 1st century CE, Pliny the Elder described a substance called sapo. He called it an invention of the Gallic provinces. It was made from suet and ashes. The best kind, he wrote, used beech ash and goat fat. There were thick and liquid varieties. But Pliny did not introduce sapo as the Roman answer to dirty hands. He described it as a preparation used for making hair red, especially among Germanic men. The word that eventually traveled into many European languages appears in Latin as a foreign technology connected with hair treatment. Soap was already chemically recognizable. Its cultural meaning was different. This is a useful warning. An invention is not defined only by what a substance can do. It is defined by what a society thinks it is for. The same mixture can be a textile cleanser, medicine, cosmetic, hair treatment, laundry product, or body soap. A modern person sees foam and imagines hygiene. An ancient user may have seen prepared wool or colored hair. The word itself preserves the journey. English soap comes through Old English sop and belongs to a West Germanic family of words related to German seif and Dutch zeep. Latin sapo also appears to have been borrowed from a Germanic source. So the language carries an old reversal. Rome spread roads, laws, baths, and Latin across Europe. But the Latin word for soap may have entered the language from peoples Rome called outsiders. To become the familiar bar in your hand soap needed more than fat and ash. It needed predictable raw materials, large vessels, skilled boiling, separation cutting, and time to dry. In regions rich in olives, plant oil offered a different foundation from animal tallow. Olive oil soaps could become hard, pale, durable products when made with suitable alkali and processed carefully. Living traditions in the Eastern Mediterranean preserve the complexity of this craft. Nabulsi soap from Palestine is made from olive oil, water, and lye. UNESCO describes a process practiced by families and workshops in which the ingredients are cooked. The finished mixture is poured across a floor, allowed to cool, cut into cubes, stamped, stacked, and left to dry. The dramatic moment is not the boil, it is the floor. A hot liquid becomes a broad, pale sheet. Workers step across it in a planned pattern, cutting, intersecting lines. Individual bars emerge from one continuous surface. Then the bars are stacked into tall, ventilated towers so air can reach them. The soap may remain there for months. Nothing inside the formula is fast. Olives must grow. Oil must be pressed. Alkali must be prepared. The batch must cook. Water must leave the bars. This slow process turns local agriculture into stored cleanliness. It also turns soap into identity. Knowledge passes through households and workshops. The person stirring the kettle recognizes stages that an outsider sees only as a thickening liquid. The cutter knows how far the blade must travel. The stacker builds shapes that will not collapse while allowing air to circulate. No single region can claim every form of hard soap. Mediterranean, Islamic, and European soap-making traditions influenced one another through trade migration, conquest, and craft transmission. But these workshops reveal a crucial step in the invention. Soap became an object. It could be stamped, counted, stored, transported, taxed. A soft paste used near the place of production is a local technology. A hard bar can travel through an economy. Once soap moved, as merchandise cleanliness became dependent not only on chemistry but on access. Who could afford the oil, who controlled the alkali, who owned the furnace, who paid the tax? The bar in your hand was no longer only a cleaner. It was compressed land, fuel, labor, and political power. By the 18th century, Europe wanted more alkali than traditional sources could easily provide. Soda ash sodium carbonate was needed for soap, glass, paper, bleaching, and other industries. Much of it came from burning particular plants and seaweed. The supply was limited. The quality varied. And growing demand made the shortage a national problem. In 1783, the French Royal Academy of Sciences offered a prize for an economical method of producing soda ash from common salt. Nicolas Leblanc found a practical answer. His process reacted salt with sulfuric acid, then treated the resulting material with limestone and charcoal to produce soda ash. In 1791, Leblanc opened the world's first factory using the process. This should have been the triumphant discovery scene. Instead, the factory became trapped inside the French Revolution and war. Sulfuric acid was redirected toward military needs. Production stalled. In 1794, The state seized the plant and suspended the patent. Leblanc regained the ruined property years later, but he never received the fortune or recognition his process eventually generated. He died by suicide in 1806. After his death, the Leblanc process expanded. Factories could produce soda ash on a scale plant burning could not match. That lowered one of the major barriers to industrial soap making. But the process carried a hidden cost. It released hydrochloric acid gas and produced solid waste rich in calcium sulfide. Manufacturers sent fumes through tall chimneys or into the environment. Vegetation suffered, waterways were damaged. Industrial cleanliness created industrial pollution. Later, Ernest Solvay developed a more efficient process. His first plant began production in 1861 and exploded. He rebuilt it. By 1869, he had overcome many of the pressure, temperature, and equipment problems, creating a system that eventually displaced much of the older Leblanc industry. These stories reveal what changed. For thousands of years, soap makers managed variable alkali from living plants and ash. Industrial chemistry separated alkali production from the local landscape. Cleanliness could now be manufactured in quantities large enough for expanding cities. But cheap soap was not created by one better bar. It was created by factories that transformed salt, limestone, coal, capital, and pollution into a reliable chemical supply. The invention of soap had entered its industrial phase. Even when soap could be produced, governments could make it expensive. In Britain, soap carried excise duties. The tax raised substantial revenue, but it also placed a cost on an everyday material used for laundering and personal cleanliness. Manufacturers operated under official supervision. The state had a financial interest in every legal batch. In 1853, Parliament debated the repeal of the soap duties. Speakers described the tax as a burden on health comfort manufacturing and the physical condition of the population. The duties were said to bring in around £1 million a year. That figure explains why repeal was politically difficult. Cleanliness competed with revenue. When the duties were removed, soap did not instantly reach every person equally. Water access, housing, fuel laundry facilities, wages, and social expectations still mattered. But taxation had been one barrier that made washing more expensive. Industrial production and changing public culture pushed in the same direction. Soap manufacturers became large businesses. Packaging made bars recognizable. Advertising connected soap with beauty, health, respectability, family care, and social class. A product once used primarily for textiles could be sold as a moral object. Clean skin came to suggest self-control. White laundry suggested competent housekeeping. Odor became evidence not only of labor or poverty, but supposedly of personal failure. This was not a neutral improvement. The cleanliness movement brought genuine health and comfort benefits. It also turned access to water and soap into a judgment about character. A wealthy household could purchase fuel private water-time servants and commercial soap. A poor laborer might be condemned for dirt created by the conditions of work and housing. Soap changed social vision. Dirt became more visible because removal had become more possible for some people. The bar could now separate not only oil from water, but respectable from disreputable civilized, from supposedly uncivilized employer, from worker and buyer, from those who could not afford the product. Mass soap improved life. It also gave societies a new language for shame. The invention had moved beyond chemistry. Humans were no longer asking only whether soap cleaned. They were using cleanliness to decide what kind of person stood before them. For most of soap's history, people judged cleanliness through the senses. Does the cloth look brighter? Does the skin feel less oily? Has the smell changed? Soap succeeded because it removed visible and tangible contamination. Then science revealed dirt the senses could not detect. Microorganisms could move between bodies without producing an immediate stain. A clean-looking hand could still carry danger. This did not mean soap suddenly became a disinfectant that killed everything it touched. Plain soap often works through removal. Modern health guidance explains that lather forms micelles that trap dirt chemicals and microbes so that friction and running water can carry them away. The same two-faced molecular structure that surrounds grease can help detach material clinging to skin. The invention designed to solve oil's resistance to water became a defense against organisms its creators did not know existed. The chemical understanding also deepened. During the 1810s and 1820s, French chemist Michel-Eugène Chevreul analyzed fats and soaps and helped establish the modern chemistry of fatty acids. He showed that fats were not single simple substances. Their components could be separated, studied, named, and related to the products formed during saponification. Soap makers had controlled the reaction for millennia. Chemists finally began explaining what the craft had been doing. This changed authority again. The experienced maker had judged a batch by texture, taste, smell, and behavior. The laboratory could identify composition. Industry could standardize raw materials. Governments could regulate products. Doctors could connect washing to disease prevention. Yet, the modern explanation returns to the ancient problem. Water cannot efficiently remove grease by itself. Many microbes and particles travel inside or alongside oily material. Soap allows water to take hold of what the skin would otherwise keep. That makes the final movement essential, rinsing. A micelle carrying dirt is useful only if it leaves. The soap molecule is not a prison, it is transport. This is why a bar can be ordinary and astonishing at the same time. It does not need to identify every threat. It does not need to know whether the material is soot, animal fat, pesticide, or a microorganism. It changes the relationship between the surface and the water. Soap protects through a form of organized letting go. Return to the hide beside the river. Water is moving across the greasy surface and doing almost nothing. Then you add the strange mixture from fat and ash. The oil begins to break apart. Cloudy material enters the water. The hide is not perfectly clean. The mixture may still be harsh, but a boundary has changed. Something that clung can now leave. That is the real invention. Humans did not create soap once. They assembled it in stages. Prehistoric communities discovered plants that foamed and materials that absorbed oil. Textile workers learned that alkaline mixtures could strip grease from wool. Mesopotamian scribes recorded cleansing processes in clay. Craftspeople learned to combine fat and alkali without leaving the product dangerously caustic. Mediterranean workshops turned local oils into bars that could be stored and traded. Industrial chemists made alkali cheap enough for mass production. Public health systems eventually understood that washing could remove threats invisible to the eye. At every stage, soap meant something different. A wool treatment, a medicine, a hair preparation, a laundry material. A luxury, a taxed commodity, a symbol of respectability, a public health tool. The chemistry remained remarkably simple. A molecule with two allegiances. One side joins water, the other joins oil. That structure is why the substance works. It is also why soap offers such a precise metaphor for human invention. Humans rarely defeat a problem by overpowering it directly. Water could not command grease to dissolve. So we created an intermediary capable of belonging to both worlds. Soap does not force oil to become water. It builds a temporary structure in which they can travel together. There is one final fossil hidden in the word. Pliny's Latin sapo referred to a Gallic and Germanic preparation made from fat and ash, used especially on hair. English soap belongs to the same broader Germanic word family. The name of the object remembers that Rome did not own every technology it recorded. A substance associated with people beyond the empire's cultural center eventually became one of the most universal objects in human life. So, how did humans invent soap? Not because one person wanted bubbles, not because an ancient city suddenly discovered hygiene. We invented it because grease carried dirt that water could not reach. We learned that ash could transform fat. We learned to control a reaction dangerous enough to burn us. And eventually we created a molecule that could take hold of what did not belong and persuade water to carry it away. The first soap did not make humans clean. It gave humans a new power, the power to make dirt let go.